Okay, we've already discussed Lenz's law, but now and we've also talked a little bit about how light is considered a ray here. Now we're going to use those two ideas together to understand how lenses work, how they do their thing, which is usually to focus or defocus light in some way or another. We've all seen this idea where we've all seen this fun little activity where you take a magnifying glass and burn a hole through a piece of paper. And the reason that you can do that with a magnifying glass is because it is a piece of glass that has been cut in such a way that it's like cutting the side off of a sphere. It's a spherical lens, we call it. And this spherical lens, as the light hits it, coming in at different angles, it focuses the light to a single point, or nearly to a single point. Out towards the edges of the spherical lens, it bends the light more. Towards the middle of the lens, it bends it less. But in the end, they all bend towards the same point. Now, if we take a cross-section of this lens, this is what it looks like. And sometimes it's spherical on both sides. Sometimes it's just spherical on one side. Sometimes it's convex on both sides like this. Sometimes it's concave on one side or convex on the other. Sometimes it's convex on both sides. But the spherical lenses come in all kinds of different configurations. This is just one of them. And this one is designed to focus light that's coming in parallel. It doesn't have to come in parallel, but if it is coming in parallel on one side, so all the light rays are coming in parallel to each other, this lens is designed to focus them at a point that we call the focus of that lens. And that is determined by two things. It's determined by the curvature of the lens, and it's determined by the material that the lens is made of. So the material of the lens that the lens is made of course, determines the refractive index, the index of refraction. So it determines how much the material turns it when the light encounters it at some angle. And then the curvature also determines how much it turns it, because it will, the light will encounter the surface at a different angle if the curvature is different. So both of those things are involved. For your typical lens, which your typical lenses are made of glass or plastic and have a index of refraction right about 1.5-ish. So for your typical lens, your focal length is about half the radius of curvature of the lens. And I don't know if you got to that part in your lab work where you were measuring the radius of curvature of the lens, but you measure the radius of curvature of the lens a couple of different ways. There are tools for doing it, but you can also use the compass that I gave you in there to draw a circle that is the same curvature as your lens. So you just kind of keep drawing circles till you have one that's the same curvature, and then try to match up your lens with one of those curvatures, and that will give you the approximate curvature of the lens. But the radius of that curvature is usually about twice the focal length of the lens, and that's also the same for mirrors. For mirrors, it is exactly twice the focal length. For lenses, it depends on the material. So we don't usually talk about the radius of curvature so much with lenses as we do with mirrors, because with mirrors, it is exact. With lenses, it may not be. But anyway, the focal point, or the focal length, is this distance that we label little f. The focal point is labeled with big F there. And for a converging lens, or a lens that is focusing light, that light is going to get focused on the opposite side of this here. And for parallel light coming in, but light is not always parallel coming in, so we're going to have some different things going on. We'll have different ways to deal with that. But there are also different kinds of lenses. Also, you have diverging lenses, which focus it the other way. For either kind of lens, we use this, the power of a lens is 1 over the focal length of the lens, and that's used usually in optometry when you're doing glasses, for example. This is the number when they talk about diopters. That's the number they're talking about, 1 over the focal length. And here we have an example where we're going to use that really quick. We're going to calculate the power. We'll calculate well, figure out the focal length of the lens. So how do you figure out the focal length of the lens? You take light that's coming in from a long distance away, because light that's coming in from a long distance is usually parallel light. Why is it parallel light? Why are the light rays coming from a long distance object parallel?
Because the ones that at such a large distance, they're going to spread out, or we only have one for
That's right. If they're not parallel, if those light rays are going at any angle and they're far away from you, they're never going to hit you, because the light rays that are going at an angle are going to go way off in space on the other side of you. So you're a small object far away from another object that is emitting light, you're going to get pretty parallel rays of light that actually hit you. Everything else is going to miss you because it's at an angle. So if you have if you've got this source of light that's a long ways away, like the sun or even the lights in this room, really, for a lens that's an inch or two big, you're going to get parallel light rays, and you can actually determine how long, what the focal length of the lens is. I've got a lens here. Here's a 2-inch lens. Okay, so tell me what the focal length of that lens is. No, you got a light right above you. But you really want it to focus, right? So you want to look for an image that's as sharp and as clean as possible. So what's that distance? 10 centimeters, 15 centimeters? And it's easy to move it. If you move it up and down or back and forth from your light source, then you'll be able to see where it focuses, because usually your image will get as small as possible at the focus, and when you're too far or too close, it gets bigger and fuzzier. Should be able to see some sharp lines from the tubes of the light. Right about there, it looks like. What's that? Yeah, so that looks to be about, I'd say 15 centimeters, somewhere in that range. So that one has got a focal length of 0.15, right? Ish. And you could measure it much more cleanly. Here they determined that it's 8 centimeters for their lens in this example. And then they calculate the power of the lens by taking 1 over that in meters, so 1 over 0.08, and you get a power of 12.5 diopters. Now diopters can be in positive numbers or negative numbers, and so can focal lengths. So a focusing lens or this convex lens like you have, which is also called a converging lens, focuses light, and it has a positive focal length, and it has a positive power in positive diopters. However, diverging lenses, which are usually the convex lenses, concave lenses rather, and they're often called negative lenses, have negative focal lengths and have negative powers in negative diopters. So, can you tell what kind of glasses I have? Positive lenses or negative lenses?
Negative.
How can you tell?
Because they curve outward on the back, and also.
Yeah, if you look at them, you can see that they're a concave lens, right? And most people's glasses are. And the way that you tell that, if it's concave, is not by looking at one side, because one side of the lens is always concave. But what you do is you look at the edges of the lens. If the edges of your lens are thicker than the middle of your lens, then you have a wider lens on the outside and a skinnier lens on the inside, and that is concave. And most people are nearsighted. Nearsightedness is the common thing for eyes. About, I think, 90-something% of people are nearsighted. So they have these concave lenses, which are negative lenses. So these lenses actually don't focus, and you can try to focus light with them. Try to focus those lights from the room onto your paper. Can't do it with these lenses, with your lenses if you're nearsighted. If you're farsighted, then you will have the opposite. You will have focusing lenses. And it's actually even easier to tell when you're looking at someone's face through their glasses. If you look at someone's face through their glasses, their face actually defocuses. It actually gets you'll see a little gap between their glasses and their face where their face gets a little smaller in there. So it demagnifies their face essentially. And so if you look on my right side especially, you can see this. The edge of my face here is kicked in a little bit. It's pretty obvious with my face. Not as obvious with Packer's because his eyes aren't as bad as mine. Especially my right eye though is quite bad. And so so you can usually tell. If somebody is farsighted, it's really obvious because they've got that bug eye effect in their glasses, where their eyes are super magnified and their face is super magnified in their glasses. And so that one becomes quite obvious. And it's very rare when you meet somebody like that. Very rare to meet somebody who is farsighted. I always like to mention though that it's a funny little joke in the Harry Potter books that the lady who's the prophet or the seer, what's her name? Trelawney. She is farsighted, and you know it in the book because she has magnified eyes in her glasses. So to be a seer or a prophetess and to be farsighted is just kind of a funny joke. But anyway.
Sometimes I wonder if that was intentional.
Oh, that was definitely intentional. So anyway, here's another one. Here's the negative lens that like we have in our glasses here, where you have the light coming in parallel rays and it actually defocuses, but it still actually kind of focuses, you could think of it. It defocuses to its negative focal length. Remember with the positive lens, we had something focusing towards the focal length or towards the focal point. This one defocuses using these rays, and it defocuses so that if you take that final ray coming out and back trace it behind the lens, it will, in those rays, those defocused rays will actually intersect at the negative focal length. So a positive focal point is on the opposite side from where the light goes in and the light focuses towards it. A negative focal length is on the same side of the incoming light and the light defocuses but lines up with that focal point still. So called a diverging lens or a negative lens. Usually we call them just negative lenses in physics and optometry and other places like this. They're just called positive, negative. Positive focuses, negative defocuses. Now the interesting thing is that if you put a light bulb at the focus of a focusing lens, it actually does the other, it does the almost, you can kind of think of it as the opposite. You have light that's coming out, but it's not coming out since the light is so close to the focal point or so close to the lens, it actually is not coming in parallel. It's coming out in a radial fashion like light does from the source, and then the lens will focus it. So if you put the source at the focus, you get this opposite effect, and that's what happens with this projector. This projector, they put the light source, which is like it's like a little really bright TV screen in there, and they put that at the focal point of the lens system inside the projector, and then it projects a parallel light outward. Now it's not exactly parallel. We know this because if you move the projector back, the screen gets bigger, right? It's not exactly parallel, but that's an artifact of the spherical lenses. Spherical lenses don't produce perfectly parallel light, unfortunately. Some do better than others, but anyway. So now we're going to talk about ray tracing, which is going to be something you're going to need to know for the lab experiments you'll do next. Ray tracing is this method that we use to determine where we think things will be focused to, because when you have light coming in parallel, we know that it focuses at the focus for a converging lens, and we know that it diverges kind of relative to the focus for a diverging lens or a negative lens. But what if that light's not coming in parallel? What if we have no idea how that light's coming in? There is a way to do this. And so the way that we do this is the first thing we do is we assume that our lenses are all thin lenses. And so what that means is that the thickness of the lens is not going to affect the outcome. In reality, that's just never true. But this makes this method possible. And it's a pretty good method. It still works even if your lenses aren't perfectly thin. But we're going to have we're going to have three things happen. If light comes in parallel to our lens, it will focus to the focal point. That much we know. That's the first thing we're going to say. If it comes in parallel on a negative lens, it will defocus relative to the negative focal point. And so that's the first rule we're going to kind of think about. The other thing that we know, and this may not be obvious to you, but it is true, if the light comes in at any angle, if it doesn't matter what the angle is, if it comes in at any angle and goes through the center of the lens, it's just going to go straight through if it's a perfectly thin lens. And that's because at the center of that lens, what you get is essentially a flat piece. It's like a flat piece of glass. And it might turn a little bit going into the glass, but when it comes out of the glass, it will turn back to its original path. And if it's a perfectly thin lens, it will just go straight through. So going through the center of the lens, right here, you're just going to get a straight through path. So those are the those are the two rules that we're going to use. And then we're going to use those rules. And here they have them. A ray entering a converging lens parallel is going to pass through the focal point. A diverging lens is going to diverge as if it was coming from the focal point. And then when going through the center is going to not change direction. Now, they have these other two, 4 and 5, which are kind of the inverses of 1 and 2. A ray entering a converging lens through its focal point will exit parallel. And a ray entering a diverging lens toward the focal point is going to exit parallel. So those are the opposites of 1 and 2. But those are the rules for ray tracing, and now we're going to use them to determine what light does in different situations. So here's a representation of each of those rules. If it comes in parallel, it focuses to the focal point on a positive lens. If it goes straight through the middle, it just goes straight through the middle. If the light goes through the focal point on the one side of the lens and then hits the lens, because there's a focal point on both sides of the lens, if it goes through the focal point on one side of a positive lens, it will come out parallel. Now, if we use all three of those rules for this positive lens and put them all on top of each other, these three lines, the one that goes parallel and then focuses, the one that goes straight through the middle, and then the one that goes through the focus and then goes parallel, will all cross at one point. And what that means is that the light from the head of our object is this person here, the light that's coming from the head of this object is going to focus over here where we have now an image. And notice that it focuses on the opposite side of this center line going down the middle of the lens. This center line is what we call the axis of the lens, the optical axis of the lens. So, in other words, this lady is standing on top of the optical axis, and the light coming from her head is focusing underneath the optical axis. That means that we're going to form an image of this object, but this image is going to be flipped over, or what we call inverted. Okay? Also notice that the image is smaller because the distance from the optical axis to where these three lines converge is smaller. So we get what we call a demagnification, or a magnification that is less than 1. Okay? Also, the magnification will come out as a negative number because it's flipped over and it's inverted. Well, how do we calculate that magnification? Well, there's a couple of different ways to calculate that magnification. One way is to just take the initial height, the image height over the object height, and that's one way you can get the magnification. But another way to get that magnification is to use the distances from the center of the lens. And the distances are always measured from the center of the lens. The distance to the object and the distance to the image. If you take the distance to the image divided by the distance to the object, and then throw a negative sign on it, you will also get the magnification. Now, distances for positive lenses are always measured as positive from the lens to the object. That's always a positive number. But from the lens to the image is positive only if it's on the opposite side of the object. If the image is on the same side of the object, which it can be, then it becomes a negative distance. So these are things that you kind of have to keep track of. Lots of things to keep track of. Also, for a positive lens, if your object and your image are on opposite sides of the lens, for a positive lens, that image is called a real image. Why is it called a real image? Real images are images that you can actually project onto a surface, that can actually be seen by anyone looking at the image. Okay? So this projector that's projecting this thing on the wall, the textbook on the wall, this is a real image because I'm projecting it on the wall. I can stick my hand in there and the image hits my hand. An example of an image that is not real is the image that you see when you're looking through your glasses. When you're looking through your glasses, you're the only one that can see what you see through your glasses, because you have to look through the glasses to see it. Okay? It can't be projected. The image that you have through your glasses can't be projected. Somebody can't put their hand out in front of your face and see something projected on their hand. It's a virtual image. They call it a virtual image when it's a non-real image. And you have to look into the optic to see it. Okay?
So
now,
when you hold the lens up and something flips upside down in the lens only, that's a virtual.
that's correct. So it's only, if you have to look into the optic to see the image, then it's a virtual image. So with a positive lens, you can create a real image by projecting light onto paper, but you can also create a virtual image by looking through it. Right? What is the image that you see in a mirror? Virtual or real?
Virtual.
It's virtual, because to see the image that's in a mirror, you have to look at the image in the mirror. For a mirror, an image is always virtual when the image is behind the surface of the mirror. In other words, you have to look into the mirror to see it. And your image is 3 meters behind the flat mirror if you're 3 meters in front of the flat mirror, right? If you're looking at a mirror, an image is real if the image is reflected off of the mirror and then projected out in front of the mirror. You don't see those very often. You have to have a positive mirror, and your object has to be within the focus of the mirror. So if you've ever been to a Hall of Science or something where they have a floating image in front of a mirror, they do this with a dollar bill in the Science Center in BYU, which is kind of funny because people try to grab the dollar bill. You can create an image like that. But it's not easy to do, but you can do it. The one that you see there, the one that see at BYU is actually technically a virtual image because you have to be looking at the mirror to see it. But you can, with that mirror, create a real image. They just don't do it. You can do it. It's just not as effective. So anyway.
Is it harder to do?
Yes, because it's difficult to create an image that can be seen. You usually have to project it into smoke or something. You have to project it onto something. It just doesn't project onto air very easily. Air is just not solid enough. It just doesn't have enough, stuff to it to really project the image. But you can do it. This is often done. This is often done in movies when they're trying to project ghostly images. They project them onto floating sheets or smoke or steam or something. So they do that with mirrors or lenses, either way. So anyway, this is what we call ray tracing. And by doing this ray tracing, actually by doing this very carefully, measuring distances very carefully, using a ruler and everything, you can actually predict where an image will show up pretty well. It's actually pretty effective method. So with your eyeball, you actually do create a real image that is upside down on your retina. It's a positive lens in your eye that focuses the light, and it focuses it down onto your retina, and it stimulates the cones and the rods in your retina, creates these electrical impulses that are sent to your brain. Now your brain knows to flip it upside down, to flip it over. So everything that we see is actually upside down, but our brain fixes it for us, and we're used to that. It just works. That's fine. No big deal. There's also a way to calculate these things so that you don't have to actually ray trace. And the equation that you use for this is called the thin lens equation, and here it is. 1 over the distance to the object plus 1 over the distance to the image equals 1 over the focal length. These numbers do have signs. For the focal length, if you're using a positive lens, F is positive. If you're using a negative lens or a diverging lens, F is going to be negative. For the distance to the object for a lens, distance to the object is always going to be positive. Okay? Unless you're using what they call a virtual object. So you can use a real image as an object. A real image can be projected through another lens or focused through another lens. And if you're using a real image as your object, then it's a negative, then it's a virtual object. So that will be a negative distance. But there are some rules for this. We'll show you the rules here in a second. Let's see. Yeah. So you have these two equations. You have the thin lens equation and you have the magnification equation. They're both involving distances and signs. So let's actually use it really quick for a simple situation, and then we'll show you the rules for signs. So here we have a clear light bulb, clear glass light bulb placed 0.750 meters from the convex lens. The convex lens has a focal length of 0.5 meter, and we are going to calculate where this image is going to be formed. The image is way over here, and we have the distance to our light bulb is longer than the distance of our focal length. That turns out to matter in this equation. If you put your object closer to the lens than the focal length, it changes things dramatically because of this equation. But it's outside of the focal length, so it's a simple one. And we go ahead and plug in our numbers. We've got an F, we've got a D object. We want to calculate D image. So we go ahead and plug our numbers in here. Our D object is our focal length is 0.5 meters. Our D object is 0.75 meters. When we rearrange this equation to solve for the D image, we end up subtracting these two, so we get 0.667 divided by meters is 1 over the D image. So we invert that, and we get 1.5 meters for our distance to the image. The distance to the image then is way over here. We use the other equation, which is the magnification equation, to calculate our magnification. It's 1.5 meters over 0.75 meters. The 0.75 meters was the distance to the object. 1.5 is distance to the image. Notice that they're both positive numbers for this lens. The object is on one side. You measure distance from the object to the lens is positive, and then from lens to image, if the image is on the other side of the object, from the object, it is also positive. So distances are positive if object and image are on opposite sides. So that's weird. We've not done that in physics yet, but that's the way it is. Physicists did not develop these equations from mechanics. And so in mechanics, we choose a direction to be positive. In optics, they just said direction is positive if the object and image are on opposite sides. If the object and image are on same sides, then it changes things. And if the object is virtual, it changes things. But anyway, we'll see that in a second. So we plug those numbers in for our magnification, and there's a negative sign in the magnification equation, so we get a negative magnification of 2.0, negative 2.0. That means that this thing is flipped over. That's what the negative means. And 2.0 means that it's twice as big as originally was. So the magnification is double, twice, 2 times. Right? So it's fairly simple. However, here they give us some examples of different images that can be created. With that top one, you've got the guy's face inverted and really tiny. Here, when you've got the guy's face right side up and his eyeball is huge. So you can get a magnification that is positive. In other words, that the image is right side up. But you're doing different things. In this case, the eyeball is inside the focal length. In this case, he's way outside the focal length. So how are we going to determine this? So here's the definition they get for a virtual image. An image that is on the same side of the lens as the object cannot be projected on a screen is called a virtual image. So that's what we mentioned before. So let's figure out how that works. They don't do let's do the ray tracing for it first. Here's the ray tracing for an object and a negative lens. We have this object is inside the focal length of this negative lens. So the focal length is whatever it is, negative 10 centimeters. For a negative lens, f is negative. So the focal length is negative 10, and we usually put it on the same side as the object. And then we have this flower that's right here. And to do the ray tracing for this, we are going to take parallel light that's going to come in from the flower and hit this lens. But instead of focusing down, it's going to defocus up, and that defocused light is going to back trace to the focal point here. So this is the diffracted ray, or the refracted ray rather, that is negatively refracted. And then we have the second ray that goes straight through, just like that. And then we could do the third one as well. The third one, however, is not terribly helpful to us. So we won't really use it. We'll just use these two. The third one would go from the focal length. Let's see if I can remember how the third one goes. The third one would go from the focal length to the flower, and then I can't remember what it does. Anyway, it doesn't matter. But we're going to just use these two rays, the one that goes parallel and then defocuses and then backtrace it, and the one that goes straight through the middle and doesn't change. Then we see where those two lines match up. We're not talking about the line that went in. We're talking about the line that focused and then that backtracing, so the dotted line. So we take the dotted line and the line that goes through the middle, and that's where our image is. Notice that our image is on the same side of the object, so it's obviously virtual. And the distance to that one will be negative because it's on the same side as the object. The distance to the object is still positive, but the distance to the image is going to be negative because it's on the same side as the object. If we had an image that was formed over here, then it wouldn't be. So it would be... And this is exactly what happens with our eye, with our glasses, if we're nearsighted. If we're nearsighted, we have an object that is far away and big, but we can't see it because our eyes are not made to see that. They don't work right. So we put on the glasses, and it brings that image, it brings that object closer to us and makes it a little bit smaller, but it brings it closer to our glasses so we can focus on it easily with our eyes. And it creates a virtual image. So right now I'm seeing a virtual image of Scott, but that image is actually closer to me than Scott is, and it's allowing that closer image is allowing my eyes, which are dysfunctional, to focus on that closer image, right?
It also makes it smaller, though, giving the illusion that it's the same distance, which is why our depth perception is disturbed out there.
That's correct. Because it makes it smaller, it maintains the illusion that Scott is far away, which is an illusion we want to have, right? We want to be far away from each other. So anyway, this is a virtual image, an example of a virtual image being created, and that's how most people's glasses do work. So let's use the equations now to calculate something like this. In this case, we now have a convex lens. So this is still actually a positive lens. And we can create a virtual image with a positive lens as well. So we're going to go ahead and use the convex lens, focal length positive 10 centimeters, like a magnifying glass. And when you're looking through a magnifying glass, you are seeing a virtual image. So let's go ahead and see what we're going to do here. We've got the distance to our object is 7.5 centimeters, focal length 10 centimeters. So our object is inside the focal length now. We have an object that we're putting really close to the lens, which is what you do with a magnifying lens, right? So in other words, in this equation, we're going to solve for 1 over di again, but we're going to have 1 over 10 minus 1 over 7.5 now, which is actually going to end up giving us, let's see, that's not right. Oh yeah, that is right. So that's going to end up giving us a negative number. Before we ended up with a positive number here, now we end up with a negative number here. So we have our negative number, we invert it, and it ends up giving us 30 centimeters for the distance to the image, which is good for a magnifying glass. For a magnifying glass, you're looking at something that's very, very close up. And your eyes cannot focus on things that are very, very close up, just like they can't focus on things that are very, very far away. Our eyes are just not meant to do that. So what this one does is it puts the image further away so we can focus. Our eyes are meant to focus at about 20 centimeters. And so 30 centimeters is not bad, but it's negative 30 centimeters, which means it's on the same side as the object we're looking at. It's actually pushed the image further away than the object. And let's see what it does for the magnification. When we calculate the magnification, distance to image over distance to object with a negative, we already have a negative for the distance to the image, so it becomes a positive 4. That means it's magnified it 4 times. It's made it much bigger and put it a little bit further away so that we can look at some detail. It makes it bigger so we can see some detail, and it puts it a little further away so our eyes can focus on it a little bit better. And that's what we do with magnifying glasses. Now, what if we do the same thing with a concave lens? The only thing that really changes is our focal length now is going to be a negative number, right? Still, if the object, distance to the object, if it's a real object, something you can touch, if it's a real object, that distance to the object is still going to be a positive number. And if the image is on the same side, it's going to be a negative number. If the image is on the opposite side, it'll be a positive number, same distance, same deal. So we'll just be calculating that. In this case, they're looking at a book that is 7.5 centimeters from a concave lens. And the focal length for those lenses is negative 10 centimeters. Plug in our numbers. We calculate the distance to our image to be negative 4.29 centimeters. And now we calculate our magnification then to be 0.571. So in this case, it moved the object was at 7.5 centimeters, and the image was at 4.29 centimeters, negative, which means they're both on the same side. The image is actually closer than the object in this case. The image is actually focused in closer than the object, just like in this example here. The image is closer than the object. That is that example, in fact. And it is going to be magnified 0.571, which means it's going to be demagnified. It's going to be less than 1, so it's about half the size. And that is what's going on. So here is a table that tells us something about some of the different situations we can encounter. They put them in the form of a few cases here. The case 1 is when you have a positive, let's see, when your distance to your object is further away than the focal length, right? You're going to get a real image, and that means DI is going to be positive and magnification is going to be negative. It's going to be flipped over, right? In case 2, now I think that F is, so the first one, F is positive, so you're using a positive lens, focusing lens. Case 2 is when you have a focusing lens and your object is closer than the focal length. It's inside the focal length, closer to the lens than the focus. Then you're going to get a virtual image. You'll have a negative distance to your object and a positive magnification. And then case 3 is when you have a negative lens and you're going to get a virtual image and you're going to get a negative image distance and you have a positive magnification. And here are the steps for solving these problems with lenses. Right? It has to do with drawing. You often want to draw out a nice ray tracing just because it kind of gives you an idea of what's happening. But you need to make sure that you get the signs correct for your focal length so that you can use the equation properly. If you don't get the sign correct for your focal length, your equation will not give you the correct sign for your distance to the image. Distance to the object, if it's a real object that you can touch, is of course always positive, so it's no big deal. Now, one thing that I hope that you realize that I didn't really mention is that, of course, there are an infinite number of rays leaving light rays leaving this flower and going through this lens. You know, we just pick one point on the flower to figure out where that one point will be focused to. It's not just, there aren't just 2 or 3 rays leaving the flower and going through the lens. Just something to be aware of so I don't confuse anybody later. Now, mirrors, image formation. Image formation with mirrors follows a very similar process, but different rules, right? With mirrors, you don't have refraction, you don't have the thin lens equation, you don't have these things. You have, what you have with a mirror is you have light bounces off at the same angle that it hit it with, right? Relative to the normal of the mirror. So if you have a flat mirror, you have the very simple thing going on that you create an image behind the mirror, the exact same distance as the object that's in front of the mirror, right? The only difference is one of them's an image that is behind the mirror. That's not the only difference. What's the other difference?
It's flipped.
Flipped what way?
Vertically. On the y-axis.
Across the y-axis? Through the y-axis? So, if you're standing in front of a mirror, and you raise your right hand, right? Which hand in the mirror gets raised?
The one on the right-hand side that you're looking at. You're right.
So if I raise my right hand, the one in the mirror doesn't raise the one that's on my left. So left to right does not get switched. If left to right
Our
gets...
perception of what would be left to right for it.
No, it's not our perception. Our perception of right is still on the right side.
If we were the reflection.
If we were the reflection, but we're not the reflection. So we're saying if physics was switched around backwards, then everything would be backwards. Of course that's true. What really changes? There is something that changes. There is something that is flipped, but it's not left to right. Look at the picture here in the book. What is flipped? It's not left to right. You can see what's flipped here. There's a label on that bottle that tells you.
It's front to back.
Front to back is flipped. So when you're looking into a mirror, you don't see the back of yourself because the front of yourself is the thing that's flipped around. The back of yourself is behind you, right? The back of yourself is, if you're looking at it from the side, the back of this bottle is on the left side, and the back of the reflected bottle is on the right side. So what's really flipped is front to back, right? It seems like left to right would be because we put ourselves in the place of our reflection and say, well, that would be my left hand if I was the reflection. But you're not the reflection. What a ridiculous assumption we make, right? We do that all the time in mirrors. This is something that we're raised to be, we're told that this is true from our very early age. That left to right is switched. And why are we told that? Because when you look at words in a mirror, they look backwards. Why do they look backwards? Because they've been flipped front to right, front to back. If you take a page and write on it with a nice dark pen, like a Sharpie, and flip it around, it's backwards. Because you're looking at it from the wrong side. That's what's happening in a mirror. When you roll up words in a mirror, we're looking at it from the wrong end, from the wrong side. It's not that they've been flipped left to right. They've been flipped back to front. Because the letters in the mirror are also, not each letter wasn't flipped left to right, right? It's that the whole message was flipped front to back. So that's the strange thing about it. If the thing was just flipped left to right, then each letter would have been flipped left to right, but the message would have still, like the word car would still start with car, would still start with C in both cases, but the letters would just be flipped. And it seems strange, but it's true. It's that if it's left to right, that's what happens. So, okay. Okay, so here is an example of ray reflection. In a spherical mirror, they don't always focus at a single point for a spherical mirror. And that is true. That is true in general, but it's more true for mirrors that are very, have a very small radius of curvature. So I have a mirror over here that has a radius of curvature of like 5 centimeters or something, and it's not going to focus at the center. If it was a parabolic mirror with a focus at 2.5 centimeters, it would focus right at that. But spherical mirrors don't focus exactly at the center. However, if the radius of curvature is large, in other words, the mirror is more and more flat, but it's still curved, then those things start to converge at a point, much more tight point, you could say. And that's where this focus equaling the radius of curvature divided by 2 becomes more true for mirrors. I think I said earlier that it's exactly true, but it's not exactly, but it is very close. So we use that a lot. And for positive mirrors, light coming in, parallel rays coming into a spherical mirror where that curvature is pretty big compared to the size of the mirror, like the actual physical size of the mirror. That is going to create these light rays coming in and focusing at that focal point. For a diverging mirror, where the mirrored surface is on the outside of the curve here, converging or parallel rays coming in will diverge away, but if you trace those back through, you're going to get them all converging at that negative focal point behind the mirror. And you can see these things, you can see these effects in these mirrors that I've got here. Actually, I think they have a picture of the book.
You have surface mirrors?
What's that?
You have surface mirrors?
Yes, I do. Oh, they don't have a picture. But I've got some mirrors here that are spherical mirrors. And like I said, they're not ideal for this because they're such a tight curve. Eventually I want to buy some that are not so tight. I thought I forgot about this one. So this one's not bad. So here's a converging mirror. As you're looking at it, it doesn't make you sick. You can see that the focal length at a point, there's a focal length where your image switches to from negative to positive. So there's my negative image. I've got a negative image there, so my head's upside down. Can you see my head? My head's upside down, and then as I move closer and closer, eventually my head is right side up. But it's huge. Huge image. And you can see it in this one actually even easier but it's harder to get the wrong. But you can definitely see the negative image there. But this one here, you get the image right side up. So this one, you see the image right side up. But your face is quite small. Right? This one, upside down, this one right side up. And so you can see how those things diverge. However, when we make the assumption that these things have this focal length that is quite defined, then we actually can use the thin lens equation again. We can use the thin lens equation where the focal length for a focusing mirror, a convex mirror, is going to be positive. The focal length for a concave mirror will be positive. Convex mirror will be negative. And if we use the proper focus in this equation, then we can calculate the distance to the image again, where the distance to the object will always be positive for a mirror. Always be positive for a real object in a mirror. Anyway. So you can use the equation again to do this. And they do this. This is the most common way to create solar power. So here is, this is how solar power is usually generated. Most people think it's like this where you have, and in fact even this one is not what it seems. This one looks like it could be, no, that one actually looks like it is. So normally when we think of solar power, we think of these solar cells that convert solar energy or light directly into electricity, which is what these do. But it's a very inefficient process. I think at the best they've done 20% efficiency. This is how it's usually done. That's not what I was looking for. Let's see, view image. I just want to look at the image in a bigger size. How can I do that? Anyway, that's good enough. So in this, what we've got here is we've got a whole bunch of mirrors. So each one of these things out here is a mirror. It's a curved mirror, spherical mirror. And actually they're mostly cylindrical mirrors. But a cylindrical mirror is just a mirror that's made of a cut cylinder. Here you can really kind of see that they're mirrors and they're reflecting this light. And this tower is filled with liquid sodium. And so you're essentially heating up this liquid sodium in the tower. Each one of these mirrors is focused on this tower. And it's liquefying this sodium and heating it up and actually turning it into a sodium steam. And then that sodium steam is used to turn turbines. You use them to turn turbines, the turbines turn generators, and you create electricity just like you would in a nuclear power plant or in a coal-fired power plant. Much more efficient. You can get up to 40% efficiency this way. So it's a way more efficient system for converting energy and a lot cheaper. The mirrors are much cheaper to make than solar cells, and you don't have to replace them, you just clean them. Here you can really see the energy being focused on that tower, that sodium tower there. That actually may be a drawing.
It's definitely a graphic, that's not real.
Yeah, it doesn't look like it's real. But there are several where you can really see it lighting up. I mean, that's one example of it. This is an actual picture where you can see it lighting up. See how much energy is focused with those mirrors on there. So that is how most solar power is created these days. And there's lots of them all over the world. No, they cannot create as much. In some places, they're better than others. For example, when you build one of these things in Arizona, it's pretty damn good. When you build one of these things in North Dakota, maybe not so good. You get a lot more sunlight in some places than others. Well, and also arid climates where you don't get much cloud cover, don't get much rain. That's the big deal. The big deal is cloud cover. You can actually run these things really well in Antarctica. They almost never get clouds in Antarctica. It almost never rains or snows in Antarctica. So these things would be great in Antarctica. You just have to build it. It'd be a problem. But getting the stuff to Antarctica would be a little bit of a problem. But you just don't want to have clouds. You want to have lots of sunlight. Let's see, where were we? Here we go. All right, so anyway, same equation though with mirrors as with lenses. You just have slightly different rules, and because with a mirror, if the image is on the same side of the mirror, that one can be projected. So if an image is on the same side of a mirror as the object, then those numbers, those distances are both positive. Now, if the image is on the opposite side of the mirror, or in other words, if it's inside the mirror, that's considered a negative distance now. And it will come out in the equation that way. So you don't necessarily have to remember it, but you do have to realize that it's going to mean something different. So now virtual images are always inside the mirror. You have to look into the mirror to see it. And real images are always on the same side of the mirror as the object because they're being reflected back to where the object is. Now, just because an object is inside of a mirror doesn't mean that it seems like it is inside the mirror. It can actually look as if it is closer to you than it is, and that has to do with that magnification thing. Magnification can make it look as if it is floating in front of the mirror, and that's how they used to make. Old flight simulators, is using big parabolic mirrors, where the images were created inside the mirror, but they were magnified in such a way so that they looked like they were coming out of the mirror. It's a very effective method, just expensive. And that's as far as we're going to go today. I'm going to turn you loose on the next parts of the experiments, let you guys do some more experiments. And then next time tomorrow we'll talk about visual and optical instruments like telescopes and microscopes, because that's the next part of your lab. You'll be starting to build telescopes and microscopes and other things like that. And then next week we'll learn about the eyeball, and we'll break out the eyeball tanks, and we'll let you pretend to be optometrists. Sound like a plan?
Yep.
All right. So go ahead and get back into your optics experiments. Still have that optics kit behind you there, looks like. Continue on with your optics lab.